Welcome to the next class of data communication networks. So today we will be talking about our unit number 3, which is network layer. So far we have discussed about the first two layers of OSI model called physical layer and data link layer. So in data link layer we try to understand the various functions performed like framing, flow control, error control. Then we talked about the functions like multiple access control. Along with this, we also discussed about the protocols like HDLs. So the next unit, that is network layer, which is the third layer of OSI model, and it lies between transport layer and data link layer. So as per the norms of OSI model, it tries to provide the services to the transport layer and it takes the service of data link layer. So what are the different functions which are performed by it will be discussed in this unit. At the same time, what are the important elements, what are the important architecture involved in the network layer, and the important protocols which are used in the network layer will be our focus of discussion. So before we start our topic, let me just give you a quick glimpse of topics that are going to be covered in unit number 3, that is network layer. So first, we are giving a brief introduction about the network layer, the services provided, and particularly we will focus on a very important function of network layer called forwarding and routing. And after this, we'll try to discuss about network service models. What do you mean by network service model? Then what are the different types of models do we have? And next, we'll also talk about the two different types of networks based on the network layer functionality. And we'll try to compare those two models, namely virtual circuit networks and datagram networks. After this, we'll try to have an understanding of one of the most important element of network layer called router. So the major function performed by a network layer is routing function, and to implement the routing function, the important hardware element involved is called router. So we'll try to understand what is a router, how does it perform routing, and what are the internal or the elements of a router. A router basically consists of four important parts, which is input processing, output processing, queuing, and routing control plane. Along with this, we'll also try to discuss about one of the most important topic called the protocol used at internet layer called internet protocol. In this, we'll try to understand how do we implement internet protocol and what is forwarding and addressing in network layer using internet protocol. Then we'll try to understand the IP datagram format, then IPv4 addressing. We'll also talk about one more important protocol of network layer called internet control message protocol, and the second version of internet protocol called IPv6. So IPv4 and IPv6 are the two versions of internet protocol which we'll try to focus in this particular unit. The major functions performed by network layer are to receive the data from the transport layer, which is in form of segments, and to convert that data into so-called datagrams. Along with this, the network layer is also responsible for host-to-host delivery. Whereas your data link layer is just responsible for node-to-node delivery, the next kind of delivery called host-to-host, that is from source location to the destination location, it ensures the data will be transmitted. That is not referred as host-to-host delivery. And to implement this, we need an additional address to the MAC address known as IP address. The MAC address changes from node to node, but IP address remains constant. That is the reason why you call IP address as universal address. So first, the data network layer of the transmitter will be receiving the data from the transport layer of the sender, and that need to be transmitted to the transport layer of the receiver. So what it does is it receives the data from the sender, encapsulates the data into datagrams, and on the receiving side the datagrams will be received by the network layer of the receiver, and it decapsulates the data and delivers the segments to a transport layer. Remember one important terminology, that the data in the transport layer is referred as segments. So a transport layer at the sender side, it receives the segments from the transport layer. and converts into datagrams, that is called encapsulation. At the receiver end, will try to decapsulate the datagram and try to forward the segments to the transport layer. So network layer protocols in every host and router examines the transport segment from header fields in all IP datagrams passing through it. So what we exactly try to mean here is that every router which is involved will be trying to understand the IP address so that it can forward the datagram to the exact destination. Now this is, let us look at this figure. This is the source which would like to transmit the data, and this is our destination which would like to receive the data. So the application layer, transport layer, network layer. So the network layer of the source would have to receive the data from the transport layer of the source, which actually receives that particular data from application layer of the source. So here the data will be referred as segment, here it is referred as datagram. So segment will be encapsulated into datagram at the sender side. At the receiver side, first the data reaches to the network layer and it decapsulates the datagram and converts to segment, which is later forwarded to the application layer. Let us look at the functionality or how exactly a datagram is transmitted. So these are all the intermediate nodes which are involved in the transmission of data from source to the destination, and all the intermediate nodes involved are routers which only function up to a layer called network layer. Let us look and how a datagram is actually transmitted. So here you could find an application layer generated the datagram data which is forwarded through all the intermediate nodes and finally reach to the network layer, and from there decapsulation happened and so you will find the segment is transmitted finally to the application. In the previous slide we were talking about two important functions which are delivered by the network layer. The first one is routing of the data from the source to the destination, which we call it as host to host delivery, and receiving the data from the transport layer and converting it into datagrams. Encapsulation happens at the sender side and decapsulation happens at the receiver side. Now in between the source and destination we had a number of intermediate nodes called routers. Now what exactly the forwarding and routing concerned with network layer meant to us? Let us try to understand. So the role of network layer is to move packets from the sending host to the receiving host, which we are referring with a terminology called host to host delivery. To do this particular function, the network layer performs two important functions. For a host to host delivery to happen, the network layer need to perform two important functions. What are that? First one is called forwarding. Let us look back in the previous slide. What happened is, between source and destination we had a number of intermediate routers. So generally router will be having different interfaces. So a packet or a datagram may be entering from the one interface, and it need to be, if it is not the end destination, it has to be forwarded to the next router or the device. So it has to go out from the router through one more interface. So whatever the datagram that is entering into a router will be entering from an incoming link, and it has, or input link, and it has to move from an appropriate output link. So this traveling of the packet from an input link of the router to the output link of the router we refer with a function called forwarding. So forwarding is concerned with how a datagram travels within the router. Then coming to the routing, routing indicates how exactly a datagram will be transmitted from the source location to the destination location. The total route which has to be followed by the datagram to reach to the destination from the source, so that host to host delivery happens, we call the total path traveled by the datagram as routing. So determining the route to be taken by the packets from source to destination is called routing. So routing is concerned with the total function of identifying the path from the source to the destination, whereas forwarding is concerned with within the router where the datagram enters from an input link and where it leaves from one of the output links. So that particular transmit of data will be referred as forwarding. Within the router, it's forwarding. But from the source to the destination, including the routers, we refer it as routing. So the algorithms that calculate the routes to be taken by the packets are referred as routing algorithms. So basically, to find the route from the source to destination, we will be having different algorithms which we refer them as routing algorithms. previously for your senior batches we used to have those algorithms in detail as a part of syllabus, but for this semester they have not included the routing algorithms. But in case if we find some time, we'll try to have a class where we'll try to cover those routing algorithms in brief, so that you can need an understanding of those different types of routing algorithms. We'll do it once time is available. After the ending of this third unit, we'll spend 1 hour on the routing algorithms as a beyond syllabus. So in the previous slide, we were talking about two important functions of network layer called routing and forwarding. Let us try to understand the interplay that happens between the routing and forwarding functions. First, every router, for instance, this is the total network where the data has to be transmitted from one source to the destination, and we have number of intermediate nodes called routers. To forward this data from source to destination, each router or every router need to have a forwarding table. How does a forwarding table appears? Like this. So here we have every router which have a forwarding table which helps in routing of the packets. So a router forwards a packet by examining the value of field in the arriving packet's header, and then so every packet it is going to receive is going to have some the header value, and then that is being monitored by the router using its routing forward table. Will be trying to find out the index. So then using the header value to the index in the routing forward table, what it happens is it will try to find out the link through which the packet has to be forwarded from the router, so which we are calling it as forwarding. So the value stored in the forwarding table entry for that header indicates the router's outgoing link interface to which the packet has to be forwarded. Now just look at this figure. Here you have number of intermediate routers connected between source and destination, and the source will be forwarding the packet or datagram to the first router. So each router in this path will have a routing forwarding table based on a routing algorithm. So look here, you have all the header values, and the second column is output link. So every datagram which is received by the router will have this header value. So what happens when a router receives a packet? It looks at the header value, and in its routing forward table it will try to compare that header value. For instance, we'll take, we received a packet with the header value field 0111. So this is here. So 011 is associated with an output link called 2. So what happens in this router is, so it has three interfaces. When it receives a packet called 0111, it identifies that the output link associated with this particular header value is 2, so it forwards through the output link 2. So this particular process implemented by a router is referred as forwarding table. Now second thing here is not just router 1, here we may have multiple routers. From source we may have router 1, this is our source, then we may have router 2, then router 3, and finally we may be connected to destination. So what is the path followed by the datagram here? S to R1, then we'll have R2, R1 to R2, R2 to R3, and finally R3 to destination. So here every intermediate router which receives that particular datagram will look at its header value and find out its output link through which that particular datagram has to be forwarded, so that it finally reaches to the destination. So the network layer responsibility starts from the source and it will be happening up to the destination host, and that is the reason why we refer it as host to host delivery. So what exactly happening here is, so each router is having a local forwarding table, and to have this local forwarding table it has to run an algorithm called routing algorithm. The routing algorithm determines end-to-end path through the network, and forwarding table of each router determines the local forwarding at this router. I hope this is clear. So along with forwarding and routing functions delivered by the network layer, there is one more important function delivered by network layer in case of virtual circuits called as connection setup. in brief, a virtual circuit is a process in which a path has to be established from the source to the intermediate routers to the destination. So, what is required here? So, the important function which is performed by network layer in architectures such as ATM and frame relays, which are actually connection oriented networks, is connection setup. So, before I want to transmit datagram from the source to destination in connection oriented network. So, what is required? A path has to be established from the source to the destination through the routers. So before a datagram is transmitted, we need to connect the two end hosts, which is source and destination, and all the intervening routers which are present along the chosen path from source to destination, and they have to handshake, means to accept that okay, we are ready to transmit the datagrams which we are going for receive through from this source to destination. So there is a need for a handshake with all these intermediate routers and the source and destination, so that this can happen before the network layer of the source starts transmitting the packets. So this particular function, where before the transmission of packet starts from source to destination, source, destination, all the intermediate routers which are involved in that particular path give a mutual agreement or acceptance, we call that particular process as connection setup, which is one more important function delivered by the network layer. So in virtual circuits, along with forwarding and routing, the network layer should also ensure the implementation of connection setup. But for connection setup to be established, the first thing has to be done is the routing algorithm should be implemented at the source, so that the path for that particular datagram is identified, and once the path is identified, all the elements including those intermediate routers are informed about the data flow that has to be happened. This is called connection setup. Right. So far we have discussed one of the important functions of network layer called forwarding and routing along with connection setup. The next topic which we would like to discuss is network service model. Network service model defines the characteristics of end-to-end transport of packets between sending and the receiving end systems. So it actually tries to explain you the characteristics of the packets that have been transported or transmitted from the sending to the receiving end systems. What are some of the services that you can be expected to be provided by the network layer? First one, let us look for individual datagrams. The first one is guaranteed delivery. What do you mean by a term called guaranteed delivery? Suppose a host has actually transmitted a data. So this particular network layer will give us a guarantee that the packet will eventually arrive at its destination. So whatever you generate, I am responsible to make sure it delivers to the destination. That particular service is called guaranteed delivery. Sometimes we need something beyond that. What is that? Not only ensuring the delivery of packet, but that particular packet will be delivered within a bounded delay. Like we people put for Pizza Hut within half an hour, or Swiggy kind, where beyond that you will get free service kind. Similarly, if you are using my service, I will be making not only ensure that the packet will be guaranteed to deliver to the destination, but also it will be delivered within a specified host to host delay bound. For instance, I say that I can transmit your packet less than 10 milliseconds. It means once I send the packet, before that 10 milliseconds, that packet has to reach to the destination. That kind of service is called guaranteed delivery with bounded delay. These are concerned with individual datagrams. Now, what are the services that a network layer can provide for a flow of datagrams? Means more than one datagram. First, in order datagram delivery. For instance, I have sent 5 datagrams. Datagram 1, 2, 3, 4, 5. And this particular service will assure that all the packets that are transmitted will arrive at the destination in the order in which they were sent. For instance, I send 1, followed by 2, followed by 3, followed by 4 and 5. At the receiver also, the network layer will assure it will be received in the same order of 1, 2, 3, 4 and 5. Now, next type of service which you can assume for flow of datagrams is guaranteed minimum bandwidth to flow. What is this scenario is, for instance, the network layers service we have been using a bandwidth of 1 Mbps. Now, when you are trying to send data at a rate less than 1 Mbps, so as long as the sending host transmits the bit, at a rate below the specified rate. So I told maximum 1 Mbps. If I am sending the data at less than or equal to 1 Mbps, all the data will be transmitted successfully and there will be no loss of packet. But remember, this happens only when the rate of transmission is lesser or equal to the maximum specified bit rate. So that is called guaranteed minimum bandwidth flow. But in case I say that I want 1 Mbps and if I send 2 Mbps of data, definitely I will lose some large amount of data. So it should be bounded less than what I have specified. Next, the guaranteed maximum jitter. For instance, in the transmitting side, I sent datagram 1. After 2 milliseconds, I have sent datagram 2. Again, after 2 milliseconds, I am sending datagram 3. So if this is the scenario at the sender, the receiver also, first I need to receive the datagram 1. After 2 milliseconds, I need to receive the second datagram. After 2 milliseconds, I am receiving the third datagram. So here, what I am doing is, I am guaranteeing the jitter, which is the delay between the two packets or the time span between the two packets. So this service guarantees that amount of time takes for between two successive packets to sender is equal to amount of time between two packets arrived at the destination. So these are the different services which you could expect to be provided by the network layer, and we call these are network services. And based on this network services, we categorize different types of models which defines the characteristic of end-to-end transport of packets between sending and the receiving end system. In the previous slide, we were talking about different types of services provided by the network layer, and based on the services provided by the network layer and how the packets will be transmitted, we categorize different types of network layer service models. The first of these models or the architecture which we are going to discuss is the one which we are using in our day-to-day life called internet. And internet is actually a best effort delivery service. What do you mean by best effort delivery? In case if I am trying to send 10 packets, I say that I tried my best, but unfortunately none of the packet reached. There also you cannot blame it because it's a best effort. It's not guaranteeing any kind that I will 100% transmit or without delay I will transmit. All those kind of things which we are talking that there will be no loss of packet, that is not guaranteed. The bandwidth which we are specifying, that is not guaranteed. The order in which we are transmitting will not be guaranteed. We may get in different orders from the transmitted order. And timing, we are expected to receive in 10 milliseconds. That kind of things will not be happened in normal internet. Internet is a best effort delivery service model. So in this, any congestion feedback. Congestion is something like when the number of data which has been traveling through the network got more, it finds a delay or it might be lost in the data. So just like our when the number of vehicles across on a road increases, it creates a traffic jam. The traffic in case of networks will be referred as congestion. And in case if a congestion occurred during the transmission or any loss happened, that will not be reported back to the sender. So the first type, which is called internet, is a best effort delivery service model where you do not get any guarantee for delivery of data or the bandwidth. There is no consistent think that always you'll get so and so bandwidth, or the order in which will not be confirmed. The timing also cannot be guaranteed. It's only something like I've transmitted and probably if everything goes fine, it may be reached. If not, because of some reason, there may be a problem. But this is not every time expected. We need something where we need more reliability and we expect the guarantees and services which are assured. In that case, we have to go for the other service models like asynchronous transfer mode, which in short is referred as ATM. So ATM, asynchronous transfer mode, is available in different options. The first one is called constant bitrate. Here, something like it's like a virtual pipe which is created, which is offering you a constant bandwidth, so you can get a constant rate. There is a loss of packets because of some reason there may be a loss. The order will be get yes. So the we can because all the packets travel through a constant rate. There is an order in which they have been transmitted, and timing also we can get a guarantee. And congestion we have a less in case of this, but still, if any case of congestion, that will not be reverted back to the sender. So no congestion feedback in case of ATM constant bitrate. The other case is ATM variable bitrate, which is referred with VBR. Now here we will have some guaranteed rate, something like If heavy traffic is there, I'll give you 512 kbps or 1 mbps. When traffic is low, I can give you 2 mbps. It depends on the traffic and the time of usage. So where you will have different rates for different periods of time, you refer it as variable bit rate. And here the bandwidth can be guaranteed to an extent. There is a loss of packets, yes, a bit, but not as much as in case of so we cannot have much loss. Very few cases you may have a loss, but the order is as per the transmitted order. The timing is guaranteed, but no congestion feedback. The third one is ATM available bitrate. So we were talking about variable bitrate, where you can have different bitrates for different periods, and constant bitrate which we have continuously for any time. Available bitrate is in between this case, where for instance in 1 hour, for some time the traffic is low, you may get higher bandwidth. The same scenario when the traffic got reduced, in that same scenario you will find a higher bandwidth again all of a sudden a dip in the bandwidth or bitrate available. So we will be provided with maximum of available bitrate, which is better than internet but not as consistent as constant bitrate. So guaranteed here is minimum compared with the other two ATM scenarios. Loss of packet, yes, it will not guarantee for the loss. Order, maybe yes, because it's still a circuit oriented pitch, and we'll have a transmission in the order in which it is generated. The timing cannot be guaranteed here because the bitrate is can be all of a sudden it may be dip, you cannot transmit the timing. Congestion feedback, yes. The only difference compared with the first three cases, here you will get a feedback on any congestion that has been happened. The last version of ATM is unspecified bitrate. You find almost similar to our internet best effort. The only difference in unspecified bitrate is the order will be the same in which it has been generated. In remaining all parameters, it is same as internet best effort. So among all this, the best version is ATM CBR. The worst version is internet best effort service. So the internet's network layer provides a single service known as best effort service. ATM's network architecture provides multiple service models, meaning that the same network with different connections can be provided with different classes of service. Okay, so this is about network service models. First, we try to discuss what do you mean by networks, different types of services provided by network layer, and now based on that, we try to categorize the network layer service models. Between the source and destination, if you're trying to transmit the data, they can happen in two ways. The first way is where you can have a connection established between the source to the destination, which is called connection oriented. And the second one is where you doesn't need any connection between the source and destination, but still the data can be transmitted. When you are talking about transport layer, the connection oriented is implemented by a protocol called transmission control protocol, whereas for a connection-less kind of service, the protocol involved by the transport layer is called user datagram protocol. We'll talk about those two protocols in detail in our unit number 4, but the same kind of connection-oriented and connection-less service can also be provided in the network layer. If you are trying to talk about the connection-oriented service in the network layer, then we are referring about a circuit called virtual circuit. And if you're talking about a connectionless service in the network layer, that will be referred as datagram. Computer networks that provide only a connection service at the network layer are called virtual circuit networks. The computer networks that provide only a connectionless service at the network layer are called datagram networks. Now, whether it is virtual circuit network or datagram network, but the service provided by the network layer is a host-to-host connectivity. That is the reason why the network layer provides host-to-host delivery. The first type of service offered by network layer is a connection-oriented service between the source to destination, which is referred as virtual circuits. In virtual circuit, the source to destination path behaves much like a telephone circuit. So both in terms of performance wise as well as the actions that happen between source to destination. What does it mean? For instance, we are trying to make a phone call on a telephone circuit. So before we start conversation, what is the first thing to be done? So we try to ring the number, then that will be passing through the network, reaches to the destination telephone number, and once he lifts the phone, a path is established. Then only you will start talking with each other. So just in a similar way, virtual circuit, before the data flows between source to destination, a path has to be established. A call setup and tear down, before the exchange of data, a call has to be set up, and after the completion of data transmission, a tear down for each call is required for the data flow. And one more important difference in case of virtual circuit is each packet which is transmitted through a virtual circuit will be carrying virtual circuit identifier, but basically in other kinds of networks like datagram network, each packet will be carrying destination host address. This important thing to be noted down. Every router on the source destination path maintains a state for each passing connection. So something like every router which is on the path will have an input port where it receives the packet and an output port from which it is forwarded. So for input port we will be having a separate identifier, and for an output port we will be having a separate identifier. And since a path has to be established and it need to be continued till the end of the call, so what we try to do in virtual circuit is we'll try to link router resources such as bandwidth and buffers may be allocated to virtual circuit, something like a dedicated resources for a certain amount of time, so that we will not fall short of services. So virtual circuit in brief is something where a path has to be established before the data transmits, and all the data has to be transmitted through that. And here the packets which are transmitted will be having an identification called virtual circuit identifier, and the resources will be reserved so that there will be no shortage of the resources. So in the previous slide we were talking about what do you mean by a virtual circuit and what are the requirements for a virtual circuit. Basically how does a virtual circuit is implemented? Let us have a look. A virtual circuit consists of three important elements. The first one is a path from source to destination. So before the data starts flow, a path has to be established from the source to destination. And here instead of using the destination address, we are going to use virtual circuit numbers, one number for each link along the path. And third one is we need to have entries in the forwarding tables of all the routers that are being used in the route forwarding and routing of the data from source to destination. We'll have a quick simple example in the next slide where we can understand all the three elements. So important things to be remembered. So here a path has to be established. We are going to use virtual circuit identifier, and for every movement of the data we have to make an entry in the forwarding tables. The packet belonging to virtual circuit carries virtual circuit number, and virtual circuit number can be changed on each link, and a new virtual circuit number comes from the forwarding table. These are the few important points we need to remember, and to understand this in better we will have a look at the example in our next slide. To understand the functioning of virtual circuit, let us take a simple example. Here we have a source S which would like to transmit data to destination D, and for this transmission it is using the service of two intermediate routers R1 and R2. So what is the virtual circuit path to be established between source to destination? Source to R1, R1 to R2, and then R2 to destination. Now look at this. Totally we have three links. Now from source to R1 we are using a virtual circuit identifier 12. Okay, this is the first thing to be noted. And a router has three interfaces in which it is receiving the data from the first interface. So the incoming interface of this is a forwarding table of router R1. The incoming interface is 1 with an incoming virtual circuit identifier number is 12, and to reach to the destination the router 1 has to forward this data to the interface 3. So the moving of this data from interface 1 to interface 3 we already actually call it as forwarding, and since we are using this table for forwarding function we call this table as forwarding table. So the incoming interface is 1, virtual circuit identifier is 12, and outgoing interface is 3. The virtual circuit identifier for the outgoing interface 3 is 22. Now similarly for the other interfaces, if incoming interface is 2, we have an incoming virtual circuit identifier as 22, so 63. If it is outgoing through 1, then we need to use 18. So if it is incoming through 3, then it is using a virtual circuit identifier 7, and if it is leaving through 2, it has a different virtual circuit identifier. But the case which we are trying to use here is incoming interface is 1, so virtual circuit identifier assigned is 12, and the outgoing interface used is 3, so we are assigning a virtual circuit identifier 22. Similarly, for router R2, the incoming virtual circuit identifier is 22 and the outgoing virtual circuit identifier is 32. So totally we use 12, 22, 32, the three virtual circuit identifiers for transmitting the data from source to destination. Virtual circuit routers maintain the connection state in the network. Well, we try to understand what do we mean by virtual circuit, what are the requirements, and how the implementation of virtual circuit happens. But let me once again recollect you that for the implementation of virtual circuit, along with forwarding and routing, one more important function called connection setup has to be implemented by the network layer. So not only it's between source and destination, but in between the intermediate nodes such as routers, the establishment and exchange of information has to happen. So in virtual circuit, the messages that the end system send into the network to initiate or terminate a virtual circuit, it may be for establishment of a connection or it may be for a termination of a virtual connection, and all the messages passed between the routers to set up the virtual circuit are known as signaling messages, and the protocols here are referred as signaling protocols. So here between source and the destination, I have some intermediate routers. I exchange the messages between the source to the intermediate routers to the destination for both establishment as well as for the connection termination. And all this exchange of messages between these the hosts and the intermediate routers, we are referring it as signaling messages, and the protocols used are referred as signaling protocols, right? So why do we need the signaling messages or protocols? First, to use to set up the connection, maintain the connection, and later once the communication is done, to tear down the virtual circuit. These are used in the ATM and frame relays. Remember, your internet is an datagram or connectionless service, whereas your connection oriented service examples are asynchronous transfer mode, frame relays, or X.25. That is the reason why we are not using virtual circuits in our today's internet. Let us try to see a simple example of understanding the concept of signaling protocols. Now here I have got a source which has to send the data, and my destination which has to receive the data, and intermediate routers which are used to connect the source to the destination. As we mentioned before, the data communication and exchange of information has to be happen. Now what is things happen? First, a network of the source would like to initiate a path establishment, which we are referring with the number 1, which is called initiate a call. So this initiate call is request is forwarded through router R1 or router 1, then it will be transmitted through one of these two routers, and then here we are using this particular path, then it reaches to next router, and finally this has to reach to the network layer of destination. So here the network layer of destination is actually receiving the call, which we are indicating with the function 2, incoming call. One is called initiate a call, 2 is incoming call. Once you receive a call, what is the next thing you expect? To accept the call. That will be indicated with the function 3. Once you accept a call, what happens? Then a path is established between the sender and receiver. Remember, here we are talking in terms of telephone circuit. So accept a call has been connected. Once a path or call has been connected, the data will be started flowing from source to destination. And here the source is sending the data flow is begin, which is indicated with the number 5. And whatever the data that has been transmitted, that will be received by the network layer of this destination, which we are referring to function 6. So this is what a signaling protocol and how it is actually implemented. I hope this gives us a clear understanding of what exactly a virtual circuit. Then let us try to conclude what we have discussed under virtual circuit. First, we discussed the concept of virtual circuit, which is a path has to be established between source to destination, and I need to involve all the intermediate routers which are involved in the path from source to destination. So next requirements is the path establishment. Along with it, we need to reserve the resources which are required. Implementation, as we discussed, here we are going to use virtual circuit identifier instead of destination address. And for different links, we are going to use different virtual circuit identifiers. We have taken a simple example where in between source and destination we use two intermediate routers, and our link is source to R1, R1 to R2, and R2 to destination, and each of it uses different virtual circuit, and we use a forwarding table. And for the communication to happen, a lot of messages need to be exchanged between source and destination as well as the routers which are involved in between. We call it as signaling messages, and the protocols used is called signaling messages protocols. So this is what we have for virtual circuits. Let us try to conclude our class here, but before summarizing what we have discussed in today's class, we started with what do you mean by a network layer and what are the important functions performed by the network layer. We talked about what is forwarding, what is routing, what is the difference between them, then what are the services offered by the network layer. Then we discussed about network service models, then the categorization of service provided by network layer as virtual circuits and datagram circuits. And in today's class we discussed about virtual circuit, its concepts, requirements, implementation, example, and signaling messages. We'll meet in the next class with the discussion on datagrams followed by structure of route.